Hello and welcome to the Discrete Mathematics in the Computer Science Department at Tennessee State University. My name is Ali Sekman. I'm a professor of computer science here at Tennessee State University. In this lecture, we're going to talk about the rules of inference using propositional logic as well as predicate logic. And this is extremely important because in the next lecture, we're going to talk about different ways of proving mathematical statements, and rules of inference will be essential tool for us in that lecture. Let's get started. Okay, so this is Comp 3010 Discrete Mathematics, and in a series of 5 lectures, this is lecture 4. We are going to keep talking about logic and proofs, and specifically we are going to focus on rules of inference. So far we talk about propositional logic, and we also introduce its applications. We talk about propositional equivalences, and then we also talk about predicates and quantifiers, especially existential and universal quantifiers, in the last lecture. Now we are going to introduce rules of inference, both for propositional logic and predicate logic. And next video is going to be introducing how to prove mathematical statements using different techniques. Okay, so what is the focus? I mean, our goal is to prove mathematical statements. Okay, what's a proof? Basically, proofs are valid arguments that establish the truth of a mathematical statement or mathematical statements. Okay, so proofs are valid arguments that establish truth of mathematical statements. So what's an argument? That's what we need to discuss. An argument is a sequence of propositions that ends with a conclusion. So we have a set of propositions that ends with a conclusion. Okay. Later I'm going to talk about statements, but right now let's stick with propositions. So I have a proposition, a number of propositions, okay, and that leads to a conclusion. That's an argument is a sequence of propositions that ends with a conclusion. And these are called premises. All the propositions, P1 to Pn, except the conclusion, is called premises, okay? And the final argument, which is the conclusion, the final argument is called the conclusion. And if the final argument, which is the conclusion, follows from the premises, that means if all premises are correct, that leads that the final the proposition is correct, that's called a valid argument, okay? And by the way, what we are going to do here, in our rules of inference, we will of course have premises like P1, P2, and so on. But in the what we are going to do in the using rules of inference, from when we go from premise 1, premise 2, and so on, we will have some intermediate steps or statements, and we are going to deduce those statements from the rules of inference that we are going to learn. Okay. So what we need to do, we have to understand the arguments in the compound propositions. We should understand a collection of rules of inference in propositional logic. That's what we're going to see, the rules of inference in propositional logic. And then we are going to understand the rules of inference in quantified statements, okay? And for example, existential quantifier or universal quantifier, what are the rules of inference for those quantifiers? And we are going to combine the rules of inference for propositional logic as well as for quantified statements, okay? So the arguments are represented using premises and conclusion. We typically draw a line, okay? And our premises are listed above the line, and our conclusion is listed below the line, okay? For example, here, this is a premise 1, premise 2, and this is the conclusion, okay? So this is the line, and we have all the premises above the line, and then conclusion below the line. I don't expect you to understand this, but I will tell you that for every person in the world, if that person is a man, then that person is mortal. That's the first premise. That's a proposition, actually. Okay. And then Man, Socrates, that means Socrates is a man. That's another premise. And our conclusion is that Socrates is mortal. Of course, we are going to learn the rules of inference to be able to come up with this conclusion. Okay. So valid arguments. We will show how we can construct valid arguments in two stages. First, we are going to use the propositional logic and then predicate logic that involves quantifiers. And the rules of inference are the essential building blocks in the construction of valid arguments, as we will see. And we will have in propositional logic, we will have inference rules. In predicate logic, we will have the inference rules. In propositional logic, plus we will have the inference rules to handle variables and quantifiers in predicate logic, okay? So this is another way. An argument is in a propositional logic is a sequence of propositions, okay? So that means we have sequence of propositions, okay? Some of those propositions may be premises, which is given to us, and some of those propositions will be derived from the premises, okay? And the last proposition will be what? The conclusion, okay? So this tells us that if all the propositions are correct, then it needs to lead to correct conclusion. So if all premises true, conclusion must be true. Otherwise, that's not a valid argument that you have, including premises and then inferred statements. Okay, here's an example. Okay, assume that this is proposition P. You have a current password, and this is proposition Q. You can log into network, and this is P. The first premise is P implies Q. This is given to us. And the second premise is P. That's also given to us. Therefore, our conclusion is P. Sorry, our conclusion is Q. So this says this is premise 1. This is premise 2. Okay. And this is the conclusion. By the way, there's a special name for this. This is called modus ponens. And we are going to see it soon. Okay. So here is the argument. This is premise 1, this is premise 2, and this is our conclusion. And this is valid. How do I know this is valid? Well, we just said that if all premises, if all propositions are correct, it needs to lead correct conclusion. That must be a tautology. So here, the first premise is P implies Q, and second premise is P, this implies Q. As long as this is a tautology, okay, tautology, that means that's a valid argument. So how can I show that this is a tautology? Okay, that's very easy. I mean, I have P and Q, true, true, false, false, true, false, true, false. By the way, there are other ways to do it, but I'm just going to do it with truth table so that you can also have some practice. True, false, true, true. That's P implies Q. And then P implies Q and P. This is P implies Q. This is P with and. True and true is true, true and false is false, false and true is false, false and true is false, right? And then I'm going to get everything right here, right there. So this guy, which is right there, this guy, which is right there, will do a conditional connective, right? So here, this is the premise, this is the conclusion. True to true is true, and these are false. No matter what Q is, if the premise is false, conditional statements will be all true. As you see, that's a tautology. So if P implies Q, is true, and if P is true, then it should imply that Q must be true. Okay, so you get familiar with that. We are going to see each one of them in detail. There are 1, 2, 3, 4, 5, 6, 7, 8 rules of inference for propositional logic. And they have some Latin names. The first one is modus ponens. If P is true, and if P implies Q is true, then Q must be true. Modus tollens, if Q naught is true, and if P implies Q, then P naught must be true. That's modus tollens. And we have hypothetical syllogism. If P implies Q, and if Q implies R, then P implies R. Disjunctive syllogism, if P or Q is true, and if P naught is true, then Q must be true. Okay, and then addition, if P is true, obviously P or Q must be true. Simplification, if P and Q is true, obviously P must be true. Conjunction, if P is true, Q is true, P and Q must be true. And the last one is resolution. If P or Q is true, P naught or R is true, then Q or R will be true. Now let's see one by one, okay? Here, if P is true, P implies Q is true, Q must be true. We just proved this, right, with the truth table. Example, assume it is snowing. Q is I will study discrete math, okay? And here is the first premise given to us, premise 1. It says it is snowing. The second premise, which is this one, premise 2, what does this say? It is snowing, P is true. Second one, if it is snowing, then I will go to discrete math. I will study discrete math. P implies Q, and the conclusion must be what? Q. If it is snowing, if this is true, and if this is true, if it is snowing, then I will study discrete math. If that is a true statement, then Q must be true, which I will study discrete math. This is modus ponens. Keep this one in the mind. Another one is modus tollens. This tells us that if Q naught is true, and if P implies Q, P naught must be true. Well, why? And we can see that P naught, sorry, we can see that Q naught and P implies Q implies P naught is a tautology, okay? And we can show it, I guess, very easily. Let's go ahead and show it. Why not? Okay, we have P, we have Q, okay? True, true, false, false, true, false, true, false. And then we have Q naught, false, false, sorry, Q naught, false, true, false, true, okay? And then P implies Q. P implies Q is true, false, true, true. Then Q naught and P implies Q. Okay. That means this column and this column. And as you see, false and true is false, 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 and this is true. Okay. And then we have P naught. P naught will be opposite of this. It will be false, false, true, true. And then finally, we have this whole statement here, and we are going to connect this guy with this guy via conditional statement or conditional connective. False, if these are false, no matter what the second one is, it's always true. And true, premise is true, conclusion is true, it must be true. So that's a tautology, okay? So here's an example. If P is, it is snowing, Q is, I will study discrete math. And if this is premise 1, I will not study discrete math. That means here, Q naught. And if this is premise 2, if it is snowing, then I will study discrete math. If this says, if it is snowing, I will study discrete math. If this is given to us by modus tollens, P naught must be true. That means we can say that it is not snowing. Okay, hypothetical syllogism. This is very, reasonable. If P implies Q, if Q implies R, obviously P should imply R, right? This is the corresponding tautology. We will get the first compound statement or proposition and second compound proposition. This is the connective that implies PR. If this is tautology, that means that's the case. And you can show it. I mean, it may take a little bit time, but let's show it. P, Q, R, okay? And just as a practice, T, 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 for true and for false, okay? And then true, 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 false, true, true, false, false. Just to show you, just as a practice, true, false, true, false, true, false, true, false. Then we have P implies Q. Okay, this is P, this is Q, and using, true, true is true, true, false is false, true, true is true, true, false is false. And as you see, these are false. If premise is false, no matter what the conclusion are, we know that's always what? True as a conditional statement. Similarly, Q implies R, Q implies R. This is Q, this is R with the same logic. This is true, this is false, this is true, this is true, this is true, this is false, this is true, this is true. Okay, and then let's see, I will have P implies Q and Q implies R. As you see, that is this row, this column, and this column with an and. True and true is true, false, true, false, true, false, true, and true. And then I will get the last statement, this one, okay? But in order to do that, I need what? P, R. P implies R. Well, this is P, this is R. True is premise, true is conclusion. So this will be true, false, true, false, and then true, 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 true. Okay. And then the last one is get this column and this column, get this column and this column, and use conditional connective. True implies true is true, false. If this is false, this is true, 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 and true. And that's a tautology. Okay, so that shows that P implies Q. If it is a premise, if this is a premise, this must be a true conclusion. This must be a conclusion. Here you go. It snows. I will study discrete math. I will get A. These are three propositions. And it says, if it snows, then I will study discrete math. That means P implies Q. This one. P implies Q. And this one, if I study discrete math, Q implies R, right? This one. Therefore, P must imply R. That means if it snows, I will get A. If it snows, I will get A. This is hypothetical syllogism, okay? Disjunctive syllogism is very easy too. If P or Q is true, and if P not is true, then Q must be true, okay? So you can easily show that this is a tautology as well. I mean, you don't have to even use the truth table for this. All right, this time let's not use the truth table, but we know directly that this one is equal to what? P naught and P, or P naught and Q. Distributive property, and this one is false. False or P naught and Q. That means this is P naught and Q. Okay, and then if I go and do this, remember X implies Y is equal to what? Is equivalent to what? Actually, X naught or Y. That's also what we know. So here, look here. this one is this guy, and this one is there. So I'm looking for P naught and Q implies Q. Well, if this is X and this is Y, this means I'm looking for X naught or Y. That means P naught and Q not or Q. Okay, that's what I'm looking for. And this means P or Q naught or Q. And Q naught or Q is always true. And P or true is always true. So that's a tautology. You don't even need to use a truth table here. So here, let's see, I will study discrete math. Q is I will study English literature. And P or Q is I will study discrete math or I will study English literature. Okay. That is premise 1. And then I have premise 2. I will not study discrete math. Okay. I will not study discrete math. In that case, I will not study discrete math. This is the case, then we will conclude Q, therefore I will study English literature. If this is the case, then this is my conclusion, I will study English literature. Addition is trivial. If P is true, P or Q is already true. I will study discrete math, I will visit Las Vegas, and this is given to us, this is P and this is Q. I will study discrete math. If I will study discrete math is true, I will study discrete math or I will visit Las Vegas is also true because this is or, right? Simplification, if P and Q is true, then P must be true. In fact, Q must be true as well, okay? I will study discrete math, I will study English literature, this is P and Q. Here, I will study discrete math and English literature. If this is true, that means I will study discrete math is true and I will study English literature is also true. Conjunction, if P is true, Q is true, P and Q must be true, okay? I will study discrete math, I will study English literature, I will study discrete math is true, I will study English literature is true. That means I will study discrete math and I will study English literature must be true. Resolution, I mean, this is also pretty simple. If P or Q is true and P naught or R is true, then Q or R must be true, okay? You can prove that this is a tautology either using truth or just regular arithmetic here. Okay, let's look at this. Here, I will not study discrete math. This means P naught. I will study English literature is R, and we have or here. So that means P naught or R. That's premise 1. That's the compound statement 1. And then I will study discrete math. I will study discrete math is what? P. I will study databases is Q, and I have or. As you see here, premise 1 and premise 2, therefore we can conclude that Q or R, and Q is what? I will study databases or I will study English literature, okay? So to remind ourselves, we have modus ponens. Modus tollens, hypothetical syllogism, disjunctive syllogism, and addition, simplification, resolution, and so on. So we have to be very familiar with that. Initially, we said that we have arguments. They consist of sequence of propositions, right? Actually, a valid argument is a sequence of statements, okay? Well, some of those statements may be premises, and some of those statements may be inferred from the premises using the rules of inference, okay? So basically, you have a statement from S1 to Sn, and then those statements are used to draw a conclusion. And I will show with examples, that's easiest. Think about this. It says that P and P implies Q. From this proposition, we will conclude that if P is true and P implies Q is true, then Q must be true, okay? So here it is. This is the premise. This is given to us. from this premise, from simplification, P must be true, and then P implies Q must be true. If this is true, simplification tells us P must be true, and this must be true. And modus ponens, if you recall, modus ponens was if P is true, and if P implies Q is true, therefore Q must be true, okay? So therefore Q must be true. Here is another example, okay? So we have those hypotheses. It is not sunny this afternoon, and it is colder than yesterday. We will go to swimming only if it is sunny. These are the premises that are given to us. If we don't go to swimming, then we will take a canoe trip. If we take a canoe trip, then we will be home by sunset, okay? So here are some propositions that I say. It is sunny this afternoon. We will go to swimming. We will be home by sunset. It is colder than yesterday. We will take a canoe trip. So considering those propositions, how do I have this compound proposition right here? If it is not sunny this afternoon, that means if P not, it implies, it is not sunny this afternoon, and it is colder than yesterday, Q. That's the first premise, right? And what is the second premise? We will go to swimming only if it is sunny. That means if it is sunny, then we will go to swimming. P implies R. That's the second one. Third one, if we don't go to swimming, then we will take a canoe trip. If we don't go to swimming, that means R not implies that we will have a canoe trip. That's S, right? And then the last one, if we take a canoe trip, we will be home by sunset. So the last one says, if we take a canoe trip, we will be home by sunset. So premise 1, premise 2, premise 3, and premise 4, and our conclusion is T. We will be home by sunset. So that's the argument. Now we are going to see if this is a valid argument or not. That's what we are going to prove right now. Given those premises, can we conclude that T, which is we will be home by sunset, is a valid conclusion? Okay. So we will start with that here. So this was the first premise, P naught and Q. So if P naught and Q is true, that means P naught must be true and Q must be true, right? So P naught is true, or simply from simplification. And the second premise was R implies P. So look here. What was modus tollens? Modus tollens was saying that if X naught, and then let's see, and then if Y implies X, then it must be Y naught, okay? If X naught and if Y implies X, and then it must be Y naught must be true. That's modus tollens. So here we start with the premise, simplification, this must be true. This first premise, you see P naught is true, R implies P is true, therefore R naught must be true by modus tollens, using this two. And then this was a premise, this is true, we inferred it from the statements. R is true, R naught is true, R naught implies S is true, that means S must be true. Remember, if X is true and if X implies Y, therefore Y must be true by modus ponens, okay? So this is true, this implies that, that means S must be true, simply. If S is true and S implies T was a promise, again, we can use modus ponens once more. S is true, S implies T is true, therefore T must be what? True. And that means our conclusion was valid. Okay, so far we discussed what? Propositional statements. Now we are going to talk about how we can handle quantified statements, okay? Because we will have some quantified statements as a sequence of statements, okay? So we are gonna introduce them now. Now that's pretty easy. I mean, look at here, for every xpx, that means for every element in the domain, P is true. For every element X in the domain, Px is true. That means for a particular element in the domain, it must be also true. That's called universal instantiation. And this one, if P, propositional function P is true for any element C in the domain, that's equivalent to saying that for every X, Px. That means for any X in the domain, P must be true. That's universal generalization. This is universal instantiation. This is universal generalization. And what does this say? For some X, Px is true. Well, it is what it is. So P is true for some element C. That's existential instantiation. And then what does this mean? If P is true for some element C, that means there is an X or there is an element in the domain for Px is true. This is trivial, actually. Existential generalization, okay? That's basically what it is. For example, think about our domain. Think about our domain to be all dogs. So our domain is all dogs, the set of all dogs. And what does this mean? This means, and by the way, Px is X is cuddly, okay? And for every xpx, that means all dogs are cuddly, right? And if all dogs are cuddly and Fido is C, which is Fido is an element in the domain, therefore Fido must be cuddly. And this is obvious. If P is true for any C in the domain or any element in the domain, it's equivalent to saying that for every X, Px. And for some X, Px is true means there is some element C for which P is true. For example, here, there is someone who got A in this class. There is someone, if the domain is the students in the class, if I say there exists an X for Px, that means there is one student, at least one student in the class who have A in the course. That means, and they can call that student A, okay? At least someone, right? Basically, it says that there is someone who got A in the class. This is really trivial. And if P is true for some element of C, we can say that it is true for, it is, there is an element X for which Px is true. If Michelle got A in the class, that means there is someone who got A in the class. Okay, let's talk about this. Show that premises, everyone in this discrete math class has taken a course in computer science. This is one premise. And another premise, Marla is a student in this class. Does this imply the conclusion Marla has taken a course in computer science? Actually, it's pretty simple. Let's say dx is x is in this class. Cx, x has taken a course in computer science. So what is this premise here, right there? That means everyone, X is the students in the school. Okay, there is a student who is in this class, who is in the. There is someone. There is a student in the school. If that student is in this class, that implies that that student has taken computer science course. That means everybody in this class has taken a computer science course. That's the first premise. Okay. And second premise, Marla is a student in this class. So basically D Marla. If you put Marla here, Marla is in this discrete math class. So that means we have those two promises, okay? Premises. The conclusion is, can we say that C Marla, in other words, can we say that Marla is in this class? Basically, this is what we are saying. Given every x, dx implies cx, and also d Marla, does this imply that C Marla? That's what we are going to show, if this is the case or not, okay? It's pretty simple. This is the premise. We start with this premise right there, okay? If this premise is true for all x's, it must be true for Marla, clearly. And this is universal instantiation. And the second premise is D Marla. This is true. Marla is a student. Now look from here. P implies Q and P. Modus ponens was saying that if P and P implies Q is true, then Q must be true. If D Marla implies C Marla, and if D Marla is true, C Marla must be true. That means Marla is a student in the class. Isn't it fun? Okay, so second example, a student in this class has not read the book. Everyone in this class passed the first exam. Someone who passed the first exam has not read the book. So we have two premises. This is premise one, this is premise two, and we have this conclusion. So we are going to check if from those two premises and using the rules of inference, we are able to get or draw this conclusion. Okay. Assume that we have CX, X is in this class, BX, X has read the book, PX, X passed the first exam. What is the first premise? A student in this class has not read the book. That means there is a student in the school, okay, who is in this class and who did not read the book. Okay, so that's the premise one, right? It says there's a student in this class, there's a student in the school who is in this class and who did not read the book. And what is the second premise? Everyone in this class passed the first exam. All the students, if they are in this class, okay, then they pass the exam. So that's the second premise, right? If a student in the school, if he's in this class or she's in this class, then he or she passed the first exam. So does this conclude there is someone who passed first exam, there is someone in the school, there's a student in the school who passed the first exam, but not read the book. So that is the argument that we have. Okay, that's the argument that we are going to have. Here it is. The first premise, second premise, and this is the conclusion. Let's see if we can do it, if we can draw this conclusion using those premises. Okay, we start the first premise. What does this say? There is someone in the school who is in this class and not read the book. Let's assume that if this is the case, from existential instantiation, let's assume that there is a person, there is a student, let's call him or her A, and that means this is true. And from simplification, this must be true, and this must be true, right? Here, this must be true right there, and this must be true. Actually, it's going to come right there, okay? Okay, so, and this was the second premise. This was the second premise. There is all students in this class passed the first exam, right? So since this is true for all students, it must be particularly true for A. C, A implies PA, okay? Now look here, this guy and this guy. CA is true, CA implies PA is true, then PA must be true from modus ponens, right? And then that's good. And from here, from this is true, that means CA is true and BA not is true. Now, this is true by conjunction and must be true. And PA and B not A is true for at least one A, that means there is someone who who passed the first exam but not read the book. Okay. That's from Existential Generalization. Socrates example, this is going to be very easy for us. Now, X is a man, X is a mortal. So what was our premises? Our premises, and the domain is all people. There is a person, for any person. If that person is a man, that's mortal. That means all men are mortal. Second premise, man, Socrates, that means Socrates is a man. And the conclusion is Socrates is mortal. So given this premise, and this is premise, can we conclude that Socrates is mortal? That's the question that we are going to have right now. And it is pretty simple. This is the premise. This is given to us. So if this is true for all people in the world, it must be particularly true for one Socrates, for anybody, and Socrates is someone in the world. So Socrates is a man implies that Socrates is mortal. And then we also have, by the way, there's a typo, obviously. We are given the premise that Socrates is a man. And now look here, P implies Q, and this is P by modus ponens. Q must be true, right? So that means if P implies Q, and if P is true, Q must be true, and Q was what? Mortal Socrates, that means Socrates is mortal. Okay, so let's do a couple of more examples. Here, Alice is a mathematics major, this is P. Therefore, Alice is either a mathematics major or a computer science major. That means P is true, therefore P or Q. Okay, this is addition, right? Okay, so second one, Jerry is a mathematics major, this is P, and Jerry is a computer science major, that's a Q. Therefore, Jerry is a mathematics major. If P and Q is true, therefore P. This is simplification, right? Simplification. Okay. And if it is rainy, then the pool will be closed. If it is rainy, P, then pool will be closed. It is rainy, therefore pool is closed. Modus ponens. If it snows today, the university will close. If it snows today, university will close. If the university is closed today, sorry, here you go. The university is not closed today, Q not. Okay, therefore P not. If you remember, this is modus tollens. Q not is true, P implies Q is true, therefore P not must be true. Okay, if it snows today, university will close. The university is not closed, therefore it did not snow today. If I go to swimming, P implies Q. If I go to swimming, I will stay in the sun too long. That's Q. If I stay in the sun too long, Q implies R. I will have sunburn. Therefore, if I go to swimming, I will have sunburn. Hypothetical syllogism, right? Okay, here's another one. Somebody in this class enjoys whale watching. Every person who enjoys whale watching cares about ocean pollution. Therefore, there's a person in this class who cares about ocean pollution. Well, let's put what our premises are and what's our conclusion. And first, let's have the propositional function. Cx, x is in this class. Wx, x enjoys whale watching. Px, x cares about ocean pollution. So what is the first premise? Somebody in this class enjoys whale watching, right? What it says, there is someone in the school who is in this class, okay, and enjoys whale watching. That's what the first premise is. There is someone in the school who is in this class and enjoys whale watching. And the second premise, every person who enjoys whale watching cares about ocean pollution. everybody, all students in this school, okay, if they enjoy whale watching, then they care about pollution. Okay, that's the second one, right? Every person who enjoys whale watching, for any student in the school, if that person enjoys whale watching, that means he cares about pollution. Okay, and then the conclusion will be, there is a person who is in this class. Okay, there is a person who is in this class and cares about pollution. So that's the conclusion. So basically, oops, sorry. Okay, so basically my question is, if we have those two premises, can we have this conclusion? Let's see if we can. Again, the premises are, this is the first premise, and this is the second premise. So, sorry. Okay, so from the first premise, what does it say? There is someone who is in this class and enjoys whale watching. Let's assume that that particular person is Y. That means CY and WY is what? True. And from simplification, this is true and this is true. That means WY is true. And the second premise says that for everybody, for everyone, WX implies PX. So that means for this particular Y, WY must implies PY. And well, from modus ponens, this is true. This implies that. That means this must be true, right? So modus ponens, remember X implies Y, therefore Y. This is X implies Y, therefore Y. So that means P of Y is true, okay? All right. And then let's see, C of Y is true by simplification. P of Y is true. We got that. That means C of Y and P of Y must be true by conjunction. That means C, Y, and PY is true. That means there's at least one in the domain for which C and P are true. And we are done. So this tells us, by existential generalization, there is someone who is in this class and enjoys and cares about air, ocean pollution. And this concludes the presentation. And as you see, this is very much fun. So far we talk about propositional logic, we talk about compound propositions, we talk about predicate logic, we talk about rules of inference. In the next lecture, I'm going to start showing you different ways of proving mathematical statements. I'll see you in the next lecture.